a little bit harder than the others, so let's do a couple of parabolas, a couple of ellipses, a couple of parabolas, a couple of hyperbolas, and then we'll do the systems. And we'll talk about the final week from today. Wow. So exciting. So exciting. All right, so the equation here, it's already written in standard form for us. And again, the strange thing about this conic form for a parabola is that we isolate the square as opposed to isolating the dependent variable. Normally, if you have something that represents a function, you would isolate the dependent variable, so you could write this as x equals negative 1/13 y squared. But in the context of conics, we do it totally differently. We isolate the square. So that one is in standard form already. The standard conic form that we're looking at here, this is centered at the origin. The vertex is the origin. And so this is the form that we're looking at there. So we identify the vertex, and then we find P. And to find P, we set 4P equal to the coefficient of x. We set 4P equal to the coefficient of x. So P will be negative 13 over 4. And then we want to identify whether it's going to open up, down, left, right. So first off, is this parabola opening horizontally or is it opening vertically? Horizontally. Is that what you said? Yeah. Oh, good. Horizontally. So when the y is squared, it's opening horizontally. When the x is squared, it's opening vertically. And then if P is positive, it's going to either open right or up. So in this case, P is negative, so it's going to open down or left. So we're going to say that it opens to the left. All right. So let's go ahead and start sketching the graph. And P is going to be the distance from the vertex to the focus. Similarly, it will be the distance from the vertex to the directrix. So the directrix is a line. Let's put the vertex up here. Now let's see, so that is a little bit more than negative 4. So 4 is 12, so it's like 3 and a 4. 3 and a 4. 1, 2, 3, 4. So the directrix will be right there. And that is the line x equals positive 13/4. So it's the absolute value of P that's giving you those distances. And then similarly, we go to the left, 1, 2, 3, 4. And the focus is going to be again between 3 and 4 away, so the focus is right in there. And then the parabola will open this way. There is our situation. So on the test, make sure that you can identify the equation of the directrix. So the directrix is a line, so it has an equation. Make sure that you can identify the coordinates of the focus. So the coordinates will be negative 13/4, 0 here. Right. So there's one centered at the origin. Not too bad. Let's do one that's a little more complicated. Let's find another one. Find another one. Let's go a little deeper into the parabola section. 25. Try this one, see how it goes. Come on, come on. Okay, so this one is not in its standard form yet, so we have to complete the square in two variables to get it into the standard form. So we have x squared plus 6x, so let's leave a blank. And then we have, that's the square. And with the standard form of a parabola, the square is isolated on the left and everything else is on the right. So I'll move the negative 6y and the 21 to the right. We have to complete the square. What will we add to the left side? 9. And how do you get 9?
Divide by 2.
Divide by 2, and then square it. So you take the linear coefficient, divide it by 2 and square it, and we have to add the same number to both sides. So on the left, we now have a perfect square trinomial. And on the right, let's see, we have negative 6y. We have to add that, so it's negative 12. If I add it correctly. The right side needs to be factored. The left side is good. Right side, we factor out a negative 6. And we have y plus 2. That's now in standard form. We have the square isolated, the right-hand side factored. That's standard form. And the vertex is identifiable then. What would that vertex be? Negative 3, negative 2. So we look at the x's to get h. We look at the y's to get k. So negative 3, negative 2. And then we set for p equal to the coefficient on the right. So we get p is negative 3 over 2 if you divide out of 2. Now we can identify what direction this opens. So first, should it open vertically or horizontally? So the x is squared, the y is not, so that's a vertical parabola, opening vertically. And then it's an opening down or up? Down. Because why? Because p is negative. P is negative. So if it opens up and down and p is positive, you know it opens up. If it opens vertically and p is negative, it opens down. If p is negative and it opens horizontally, it opens left. Opens right if p is positive. So if p is positive, it opens right or up. So let's sketch a little graph. Negative 3, negative 2. That's our vertex. We said that it's going to open down. Let's draw a super general sketch just to keep yourself oriented. Doesn't have to be very precise. P is negative 3 halves. That tells us that the directrix is 3 halves above and the focus is 3 halves below. So to find the directrix, we have to go up 1.5 units. So 1.5 units is right there. So the equation of the directrix, it's a line. So it should be y equals a constant. And what is that constant? Negative 1/2, right? Because the vertex is down at 2, and then we're going to go up 1.5 units, so y equals negative 1/2. That is the equation of the directrix. The focus, we know, is tucked inside here, and it's going to be 1.5 units from the vertex. So that focus is right about there. And the coordinates for the focus, what will the coordinates be? Negative 3 for x. It's on the same vertical line as the vertex. So negative 3 certainly. And then from the vertex right there, we're at -2, and we've got to go down 1.5, so minus 3.5, so minus 7/2. That would be our y coordinate. One more parabola, or is that good?
All right, one more. We'll do one more. One more, just for grins. Let's see. Yeah, that one doesn't look that difficult. Let's do one of these where we are given information and we want to figure out what the equation looks like. Oh, what did I do here? Get rid of that. Okay, so we have some info.
Let's figure out what the equation has to be. It's usually very helpful to draw a sketch to orient yourself, figure out how the directrix, the focus, and the vertex are all related to each other. So let's start with focus at 4, 0. There's our focus, 4, 0. And they tell us that the directrix is at -4, so that tells us a lot right there. And maybe you don't have to draw it, but it's always helpful. You're less likely to draw your parabola or your conic in the wrong direction. So that's what we have so far. The vertex has to be midway between the directrix and the focus. So the vertex has to be right there. Has to be at the origin. And the focus is always tucked inside the parabola, so we know that this opens to the right. We know that the parabola is going to open that direction. All right. What do we know about P? And is it positive or negative? Positive 4, right. Okay. So given that this has a vertex at the origin, what would the standard conic form be? Y squared equals 4px. Everybody agree? So it's opening sideways, so the y is squared and not the x. If it opens vertically, the x is squared and not the y. And it's at the origin, so it's just y and x. It's not y minus k and x minus h. Great. And not too bad. Y squared equals 16x. Okay, good. We'll grab one more of those and let you guys try it. Those can take a little bit of thought. Those are good practice. Let's see. I am a little baffled by what. Let's see. Find the vertex focus. This is what I want. That one. 21. Okay, so you guys work on this one. recommend starting by drawing a sketch, which is a really good place to start. It just helps you to orient everything that's going on. You'll see our focus is out there at 6,1. The directrix is the y-axis, x equals 0. So that tells us that the vertex has got to be midway between these two, so right about there. There's going to be a 3, 1 will be where the vertex is. Question? So x equals 0, when we're thinking about the graph of an equation, we say to ourselves, what are the solutions to this equation? What are the ordered pairs? So when we see x equals 0, we want all the ordered pairs that have an x value of 0. So if we want all the ordered pairs that have an x value of 0, that would be the y-axis. And then, of course, this is going to open to the right, or something like that. All right, and so we want to find the equation. We can identify p pretty easily. P is going to be 3, positive or negative? Positive because it's opening right. If it opens left, it would be negative. And what is our basic equation then? Given that the vertex is not at the origin, so we're going to have that shift in there. So what's the basic equation? So y squared plus 1 or y plus 1 squared? Y plus 1 squared. Everyone agree on y plus 1 or y minus 1? Because it's always opposite of what we see. We see the y value is 1, so the shift should be y minus 1. And does everybody agree that y's should be squared here and not x's? Y squared, x is not. So if we were writing our general equation down, it should look like this. Y minus k squared equals 4p times x minus h. So with parabolas, we always use h comma k as the vertex with an ellipse or a circle. H comma k is the center of the vertex here. So then it's y minus 1 squared equals 12 times x minus 3. So that would be our equation in the standard conic form. Any question on any step?
How did you find the vertex? Was it just because it was in the middle? Or like that it has to be in the middle?
Yep. So the vertex is always exactly in between the focus and the directrix. So if we know where the focus is and we know where the directrix is, we want to pick the point that's exactly in the middle. That has to be the vertex. Yep. Any other questions on that? Nice. Let's do a couple of hyperbolas also, and then we'll get to the nonlinear systems. Let's go grab a few. Actually, I could put one up here for you guys to deal with. So graph that, which means find the center, find the asymptotes, find the foci. All that stuff. Grab a couple of other ones to round them out. How about the center?
2 and negative 4.
Nope. Negative 4, 2. That's the most common mistake with the center. The x coordinate of the center must come from the x group. The y coordinate of the center must come from the y group. Yeah, that's the most common mistake, so it's good to make it today, not next week. H comes with the x, the k comes with the y. There's our center. Negative 4, positive 2. Center. Does this one open horizontally or does it open vertically? So the y's are in front, so that tells us that it opens vertically. And what I would think in my head, if you go to the simplest possible hyperbola with y's in the front, the simplest possible hyperbola with y's in the front would be y squared minus x squared equals 1. And hopefully by now, or if not by now, within the next 5 seconds, it's obvious to you that this opens up because this has y-intercepts and it doesn't have any x-intercepts. So this has to open vertically. So everybody see that there are no x-intercepts for that equation? If you let y be 0, x squared is negative 1. No solution. So this has y-intercepts. If you let x be 0, you get y equals plus or minus 1. So it has y-intercepts, but it has no x-intercepts. So that's our guide. That's how we remember that when y is in front, it's going to open vertically. So that's why we know this is opening vertically because y is in front. Okay. So then we go and we draw our fundamental rectangle. And how far left and right from the center are we going? How far left and right? 4. So we look under the x's to figure out how far horizontally we go. And so those 2 points right there are not on the ellipse. They're just on the edges of this fundamental rectangle. They're at the ends of what we call the conjugate axis. And how far up and down do we go? 2. And these are on, these points right here are on the hyperbola. So that point's on the hyperbola. We go down to, that's on the hyperbola. Those also would be called the endpoints of the transverse axis. The transverse axis is the one that connects the arches of the hyperbola. Maybe move this whole thing over a smidge. Okay, so then diagonals are the asymptotes. Our asymptotes are there and there. And the big arches for this hyperbola, something like that. There's our very rough sketch. Very rough sketch. The asymptote equations we need and the foci we need. Let's start with the foci. So to find the foci, we need little c squared. Little c is the distance from the center to a focus. So yeah, what do we do with the denominators? Yeah, we add them up. We do the opposite of the sign in the middle. So 20, so c will be 2 root 5. So it's somewhere between 4 and 5 units. So somewhere between 4 and 5 units, so it's down here and up here. So there's one focus, there's the other focus. And the coordinates of those foci, what's the x-coordinate of the foci? -4. Must be the same as the center, x-coordinate of the center. And then to get the y-coordinates, just remember that that c value, that's measuring from the center here, it's measuring that distance right there. That's little c. So little c is measuring from the center to the focus. So we're going to start with the y value for the center, which is 2, and then plus or minus 2 root 5. Those will be the foci. And then our last step, the asymptotes. Instead of y equals mx, or plus or minus mx, we deal with the quantities up here, how they came to us. So we're going to have y minus 2 is equal to plus or minus, right here 1/2. Does everyone agree? 1/2. So the rise is 2. We look under the y's and take the square root. The run is 4. We look under the x's and take the square root. So it's 2 divided by 4, which is 1/2. Plus or minus 1/2. X plus 4. Good. Good, good, good. Any questions on any step? Let's just do one of those abstract ones where they want us to generate the equation given information. Which section is the ellipse? Is it 10.3? I think it's 10.3, right? 10.2. Thank you. 10. Oh, wait, I see it as 10.3. Oh, did I say ellipse? Sorry. Thank you. I mean this. The ellipses are, if you can do the hyperbolas, you can do the ellipses, right? Because the 4 points that you find to build that square, you just connect them as an ellipse. So if we can get the hyperbola down, then the ellipse is a lot easier. All right, so let's do one of these abstract ones. Let's do that. I should probably put it on a new slide just to make plenty of space. All right. using the asymptote, a little bit tricky to get your denominators. You just draw a sketch of these asymptotes. So they're very shallow. The slope is 1/4. So we have that. So the hint is that we know that the fundamental rectangle goes through those two dots on the x-axis. And we know that the asymptotes go right through the corners of the box. So if we drew our fundamental rectangle at this stage, we would want to draw it something like that. Okay. Does everybody agree with that? So the fundamental rectangle is going to have the 16 and minus 16 on the right and left edges. The hyperbola will open horizontally. We have to get the equation now. All right, the center is at the origin, and it's opening horizontally. So this is where you should be at, right there. And one of those denominators you know for sure. Which denominator do you know? Yeah, what's that denominator? Yeah, 256. 16 squared is 256. Any idea how to get the other denominator? And how do we know how far up from the origin we're going? And what do we do with the asymptote to get that y value? We take the x value of 16. So this point right here, that's on the asymptote, and it has an x value of 16. So if we take that x value of 16 and plug it in up there, we see that the y value is 4. So right there, this has to be 0, that has to be 0, 4, that point. And then down here would be 0, -4. Okay, so that tells us that the c value, little c, is 4. No, I'm sorry, not little c. Little b is 4, so that's going to be a 16 over here. Yeah, so there's our equation. That's a little tricky, using the asymptote to figure out what that y value is. Does that make sense to everybody? Once you have the y value at the corner of the box, that's the same as the y value in the center of the box, and that's where we're looking below the y's to figure out how far up and down from the center we go. We go up 4 and down 4, that means the denominator is 16. All right. So let's go back to the systems. We did a couple of these slides the other day. We did that one for sure. So a nonlinear system, let me make a couple of comments again. If you draw a picture, it's really helpful, because sometimes nonlinear systems will have one solution, sometimes 2, sometimes 4, sometimes none. It's not quite as predictable as linear systems. And so drawing a sketch of it is helpful, very helpful. And remember that we do a simultaneous solve. Usually we use substitution. And when we back substitute to find the other letter, we always go into the easier equation. So those are the principles we're going to use. And I believe, did we do the second one also?
No, which is the first one.
Just the first one? We didn't do 6? Okay. So let's, so we've got a sketch here, and we see that there's exactly one solution. And this one says just a graph, and it might be because finding that point's a little difficult. We can take a step or two towards it. If it looks too crazy, we can just stop. The process, though, is what we want to at least get underway. So here we can solve for y or x. We could say that, actually it looks like maybe a little better to solve for x. Solve for x. I've already got 2 y terms over here. So if I get rid of that and turn it into a y term, I can collect them over there. So let's go with that. And this one might just have some weird irrational solutions. So x is going to be 4 over y. Plug it in. We have y squared minus 2y equals 4 divided by y plus 3. We have to clear the fractions, so we multiply everything by y. We get y cubed minus 2y squared equals 4 plus 3y. And this is why this one says just graph it. Because that is hard to solve. So that's why it says just a graph it here. Now, so if the only way we are going to be able to do this, we could try to figure out if there's a solution. When we look at the graph up there, it looks like that doesn't really look like it's right on an integer, does it? Doesn't really look like that. So if we went to a graph like Desmos, we could solve it using technology for sure. But this one, algebraically, is going to be a mess. So we'll stop here on this one. And you have to just sort of get to the point, we'll call it an algebraic mess. Solving that cubic equation for y, doing it algebraically is not in the cards. So that's when you have to use technology for. All right, so here is one that we don't need technology for. And again, if you draw a sketch, it helps. Helps orient you in terms of how many solutions. Let's see, let's use a fancy Parabola looking tool. So y equals x squared, and then x equals y squared is going to be very similar except rotated 90 degrees. That would be something like that. And we should get one solution. Or two solutions, actually. Sorry, two. We see 2 points where they intersect? There and there. This one is x equals y squared. This one is y equals x squared. All right. So the second equation already has x isolated. So let's just substitute into equation 1. So we're going to plug this into equation 1. So that gives us y equals what? Y squared squared. So that's y to the 4th. Can you agree? Y squared squared. Y to the 4th. Nonlinear equation. Nonlinear equation. Everything to one side and factor. Don't be dividing out a variable. GCF comes to the front. GCF is pretty easy in this case. It's just y. So we've got that. Then we apply the zero product rule. This says that y is 0 or y cubed minus 1 equals 0. This tells us that y cubed equals 1. This tells us that y is 1. There's only one real number that has a cube equal to 1. That's 1. Okay. So we've got our two y values. Go back in and figure out what the x's are. So which equation should I plug them into? This is super important. Let's just suppose we blindly plug into equation 1. We blindly plug into equation 1. Okay, if we plug y equals 0 in up there, that tells us that we have 0 equals x squared, so x equals 0. So that gives us one order again. 0 times 0. Plug in 1 for y, we get 1 equals x squared, we get x equals plus or minus 1. That gives us 2 ordered pairs. When we look at the graph, we know that this is not a solution, right? Plug that ordered pair into this equation down here. 1 for y, negative 1 for x, does not satisfy equation 2. So now let's see what happens when we plug into equation 2. So if we plug into equation 2, plugging into equation 2, we have x equals y squared. So x equals y squared. Oh, why did I erase the x? I'm trying to find the x. X equals 0 squared, x equals 0. That gives us one ordered pair, 0 comes 0. Now we plug y in. So we have x equals 1 squared, x equals 1. That gives us one ordered pair. Okay. So clearly it matters which equation you back substitute into, which is totally different from linear systems. Linear systems didn't matter at all, plug into either. So for nonlinear systems, when you back substitute, you always substitute into the equation that is going to give you less solutions. And those will be the right ones. If you plug into the equation that gives you more, you will have extraneous solutions. You can test those pretty easily. These are prospective solutions, so that means those ordered pairs should satisfy both equations simultaneously. And you check and you see, oh yeah, the second equation, or this one over here, that second ordered pair from here, doesn't satisfy both equations simultaneously, so it's an extraneous solution. The better rule of thumb, though, plug into the equation that gives you less solutions. And you don't have to worry. All right, let's take a look at this one. This one, the top equation, pretty easy to solve for y squared. So we have that y squared is going to be 4x squared plus 4. And that y squared is then substituted into equation 2, eliminating the y squared. And we have 4x squared plus 4x squared plus 4 equals 4. 8x squared equals 0. That tells us that x squared is equal to 0. That tells us that x is equal to 0. Now here, does one equation give you less solutions than the other? With this particular system, you plug the 0 in for this x in equation 2 or this x in equation 1, then you end up with the same equation, y squared equals 4. So this one's not going to matter. So we plug x equals 0 in, then we get y squared equals 4 when x is 0. So then y is equal to plus or minus 2. So that tells us that we have the ordered pairs 0, 2, and 0, negative 2. All right, so why don't we sketch a graph of this system just to sort of confirm that we're on the right track. What is the top equations graph? Top equation is what? Say again? Hyperbola. Yep. Hyperbola. So if we wrote it in standard conic form, it would look like that. The second one is an ellipse. We wrote that in standard conic form. It would look like that. So there's our system with our conics written properly. And the hyperbola up there, is it open vertically or horizontally? vertically because the y's are before the minus. The center is the origin. How far up and down do we go from the center? 2. Those are on the graph. How far right and left do we go? Just 1, and that will be for the conjugate axis. So we have, this is our fundamental rectangle. Then we would graph the diagonals. Going through the diagonals, we'll give our asymptotes. And let's see, so we've got two asymptotes. And this hyperbola opens up. Like that. All right, now let's graph the second equation. That one is an ellipse. Center is also at the origin. How far left and right do we go? 1. How far up and down do we go? 2. So that ellipse is the ellipse that just touches the vertices of the hyperbola. So we see very clearly after graphing that we have these two solutions, and that's what those correspond to. It's like the hieroglyphic or something. It's a message in another planet. All right, you guys try this one. Number 20. The galaxy is conic. For that hyperbola. Up and down 5. This side. Screech if you're having trouble. Oh, no. So excited.
Oh, okay. One square equals 1 plus 4. No, you can do it that way. And then what you want to do though, let's go to that top one. So say, okay, then I'm gonna plug in for this y squared, this x minus 4 y squared. Oh, okay, x squared is 9. Where's your x? You solved this for y squared. So then you want to plug that in for y squared. You haven't found the answer yet for x or y. Oh, okay. Yeah, if you want to do
We'll
that.
see.
Yeah, you can do that.
All right, so lots of different ways to go here. I think the simplest thing to do is to actually notice that you can just add these equations together and the y squareds drop out. That's one way. Substitution, of course, is going to get you to the exact same equation, x squared plus x minus 20. It's nonlinear, so you put everything on one side and factor. So that will be x plus 5 and x minus 4. And so that tells us that x is negative 5 or 4. Two x values. All right, now we have to decide which equation to plug it back into. Well, it doesn't look like it's really going to matter because y is squared in both. So if y is squared in both, it doesn't look like it's going to matter. So let's go with the second equation because that looks simpler. So when x is negative 5, in equation 2, we would have negative 5 plus y squared equals 4. So y squared will equal 9. So y will be plus or minus 3. And if we take x equals positive 4, again, plug into the second equation. So we have 4 plus y squared equals 4. Y will be 0. So it appears that we have three solutions. We have negative 5 comma negative 3, negative 5 comma 3, and then 4 comma 0. So let's do a quick graph and see if that makes sense. Let's see if we get that same thing if we graph it. Move this stuff out of the way a little bit. Right, that first one is a hyperbola. We divide both sides by 16. And is it going to open vertically or horizontally? So the x is in front, so it'll open horizontally. So we'll have x squared over 16 minus y squared over 16. So how far from the center will we be going? 4. And we're going to be going 4 up and 4 down as well. So we have a fundamental rectangle that is actually a square. Connect the diagonals. And we said that it's going to open horizontally, so it's opening something like this. Okay, second equation is a parabola. And what is the standard form of that parabola? If we do it in the standard conic form, we isolate the y squared. So if y squared equals negative x plus 4, we would then have to factor out the minus 1. So with the parabola, to put it in a standard conic form, isolate the square and then factor the other side. So p is equal to 4p is equal to negative 1. So p is negative 1/4. All right, and the vertex is 4 comma 0. So vertex here is 4 comma 0. And that's right there. 4 comma 0. And what way is it opening? Left. So what it's doing is intersecting this hyperbola over here in a couple of places. So that's why we're getting 3 answers. Question? Everybody agree that it opens left? So P is negative, so it opens either down or left. Because y squared and x is not, we know that it's opening left. And so we see the 3 solutions are those. 4 times 0. And if we went out to -5, we go up 3 and down 4. All right. Oh, it's time for a break. Let's take 10. Let's joking. Let's do 20. We'll do 26 together. Let's do it together. What's the obvious direction here? Solve the second one for x and plug it into the first one. That seems probably like the easiest thing to do. So 2y plus 5. Oh, I did. So let's substitute that into the first equation then. So we have 2 times y squared plus x times y. So I'm going to multiply that by y. So that's 2y squared plus 5y. Plus x squared. So we have to square that. That will be 4y squared plus 20y plus 25 equals 7. We're going to follow that. All right, collect our y squareds. Looks like we have 8 y squareds. And if we take a look at the, those are gone, and 25y. And then subtract 7 to the left. I think that gives us 18. 0. Nothing factors out, unfortunately. So now we have to try to factor this. The factor, is anyone brave enough to factor it yet? I'm going to guess. I'm guessing 4 and 2 to start. Yes. Does that work? 18 plus that doesn't work. 12 and is this one of those ones that's got a bizarre solution? Yeah. Okay, thanks, distraction. No, that's a good distraction. While I try to factor in my head. So that is x squared right there. So that is x. We're plugging it in right there. So we're squaring it. So that's 4y squared, 10y doubled, and then 5. How do we know for sure whether something factors or not? How can I do a test to check? I'm trying a couple numbers here, and all of a sudden I'm thinking, maybe it doesn't factor. What's that? The discriminant, right? We can look at the discriminant. Let's just look at that real quick, just so we don't go down a rabbit hole. So b squared minus 4ac. You should know from algebra that if that's a perfect square, then this does factor, if that's a perfect square. So b squared, that's 625, minus 4 times ac. So 4 times, what's that, 144? 4 times 144. So that's 625 minus what? 144 times 4. Minus 625. 49. So it definitely factors.
Found it.
What is it?
It's 8x plus 9 and x plus 2.
All right. Thank you.
Or, yeah,
Yes, 8y plus 9. Let's check. 16 plus 9 is 25. Yes, that works. Good job. And what was the 144 times? That was 576. Does everybody know that? So if you start trying to factor and all of a sudden you think, ooh, maybe it's not factorable, check the discriminant. Discriminant has to be a perfect square if it's factorable. Must be a perfect square. All right, cool. This tells us that y is negative 9/8 or negative 2. Then we back sub. Come back up here, and which equation should we plug into? Second one, because x is to the first power. Up above, x is squared, so that will give us 2 answers for each of these y's, which we don't want. We want the least number of possible answers. So we're going to go into equation 2. And when y is equal to negative 9/8, we get x minus, so it's 2 times that, that's going to be 9/4, equals 5. So x will equal 5 plus 9/4. That's 20/4. So that's 29/4. And then when we choose the other y value of negative 2, plug that into equation 2. We get x plus 4 is equal to 5. So that tells us that x is 1. And therefore, our final answer, we have 2 ordered pairs, 29 over 4, comma, minus 9/8. Here? Yeah. So let's see. So x minus, oh yes, absolutely. Thank you. So that should be positive 9/4. So this should be 5 minus 9/4. So it's 20 over 4 minus 9. That's 11 over 4. So that should be 11. And then for the second one, 1 comma negative 2. 1 comma negative 2. Right there. So any question on any step? Which one? Here?
Yeah.
So we're taking the negative 9/8, we're plugging it in right here, which makes it positive 9/4. Subtract the 9/4 to the other side. Bless you. Get a common denominator of 4, that's 20/4. 20 minus 9 is 11/4. All right, that one. You guys go ahead and try that one.
It's a fraction.
Okay, so we have that. Most of you got to that point pretty straightforwardly. So at this stage, you have to clear that fraction out, so you have to multiply through everything that's multiplied by y squared. And that's going to generate a fourth order polynomial. We have that. Nonlinear, so everything to one side and factor. So we'll put everything on the left, so the y to the fourth is positive there. And then this factors pretty nicely, 16 and 4. So this tells us that y is equal to plus or minus 4 or plus or minus 2. So each of those four y values gets plugged back in to get an x value. If we went into the top, each y would give 2 x's. Not good. Second equation, each y will give 1x. So that's where we want to go. We want to go to equation 2 right there. So we can just sort of write down all these y values here. 2, -2, -4 and 4. Then the x value will be, if y is -2, -2 goes into there -4 times. If y is 2, then that's 4, -4, that's -2, and if y is 4, that's 2. So that gives us our 4 ordered pairs. That make sense to everybody? So, 4 solutions. The top equation is what? Let's see. Ellipse and actually a circle, because it's got the same denominator as if you divide it by 20, so it's circle. Anyone? If you have an ellipse, it's got 2 foci. As you take that ellipse and you make it more circular, those foci get closer and closer and closer and closer together, and then for a circle they become the center. Second equation is actually a hyperbola. It's a hyperbola that's tilted though. And so our graph we've got a circle, and that circle is centered at the origin, and then we've got this hyperbola that is like that, and so that's where, oh, yeah, 4 answers. So we've got all 4 answers. It's kind of like that. So at this stage, we won't, once you get into higher level math courses, you deal with these hyperbolas that are rotated. And we can graph it because we know how to graph the reciprocal function. But we wouldn't know how to find the foci and the asymptotes for this very easily. Well, you can find the asymptotes for this one, but not foci. Okay. All right. Let's do this one. There's a couple of ways that could make this more complicated than you need up here. The key is this mixed term, this xy term in each. If we multiply the top equation by 3 and the bottom equation by 2, we could subtract the equations and get rid of that mixed term and have just y's. So we want to, I wouldn't recommend in this equation solving for x. It would be really messy. So here our technique will be to use elimination, which sometimes we do, but most of the time with nonlinear systems we don't. So if we multiply the top equation by 3, we get that. And then let's multiply the second equation by -2. So then we would have -6xy plus 4y squared equals -8 multiplied by -2. Now we can add those equations together and get some nice cancellation. So the xy, the mixed terms go away. We get 13y squared is equal to 13. Y squared is equal to 1. So this tells us that y is equal to plus or minus 1. Then we have to back sub to get x. You think it matters which equation here? Nah. Both of them have an x to the 1, so both will be equally pleasant or equally unpleasant to use. So if y is equal to -1, let's go into the top equation. Y is -1, we get -2x plus 3 equals 7. We end up with -2 comma -1 as our order pair. Plugging in +1 for the same equation, we'll get 2x plus 3 equals 7. So 2x will equal 4, x will equal 2. Our ordered pair is 2 comma 1. So those are our two ordered pairs, our two solutions. Now these are two that I wouldn't recommend trying to graph those by hand, because they've got that mixed term. With that mixed term, that kind of throws everything off. But you can type this into Desmos exactly as it is. You can just type in 2xy plus 3y squared equals 7, and it'll graph it. And when we look at that, it's not obvious what conic it is. It is a conic, we just don't know which one. It's not totally clear which one it is. Might be interesting to at least graph one of those equations just to see. Anyone have a guess for what those conics might be?
Anyone want to guess?
Right.
You say parabolas. Let's find out. This could be interesting. Could be interesting. 2xy. Anyone else want to guess? A tilted hyperbola. With that mixed term, it's I was going to say it's a really good chance it's tilted. And what is it? Well done, John Paul. A tilted hyperbola. I mean, that was so fun, we might as well look at the other one. Let's see, shrink, don't go too small. Let's see if that one, 3xy minus 2y squared equals 4. Same concept, right? So if you look really carefully, we're going to have one solution there, and that blue curve is going to stay below the red curve all the way to infinity. So the two solutions that we found are just these two. 2, 1, and -2, -1. Do those match what we found?
It better. Better match. All right. So let's take a look at this one that has a note next to it. Don't maybe don't see that. All right, so solve that one. Be careful. Each step of the way. You gonna get the answer yet? Don't worry. Make sense? All right, so you should be having all sorts of chaos happening. Anyone know what the answer is? No solution. Right, no solution. This top equation is that ellipse right there. What is this equation? It's a line with slope 1 and y-intercept 8. So that line is, like over there. So, yeah, no solution. So you're going to see that as you get down in there, and you're going to get, you'll end up with some sort of contradiction that should give you an indicator that there's no solution, square root of a negative or something. And if you come down and get to a point where you have a contradiction, like 0 equals 1, then you know there's no solution. Go ahead and go back and look at the system and see what's going on with it. And so when you get down to your chaotic spot, and you come back up here and look at it, you realize that once you graph it, that you should have no solution. There's no ordered pairs that are common to both. Okay, let's do a couple of these conceptual ones. So the top one says that the graph of a nonlinear system consists of a line and a parabola. The system has 2 real number solutions. True or false? Certainly can have 2, but does it always have 2? No. So by now we're really good at visualizing what's going on here. So if we have a line and a parabola, you can all imagine a system where there's no solutions, there's 1 solution, or there's 2. So those are the only cases here. You're either going to have 0, 1, or 2. No more. Only 2 choices. Okay, how about the second one? This says the graph of a nonlinear system consists of a line and an ellipse. Is it possible for the system to have exactly 1 solution? True? So we imagine a tangent line or something. And so we've got our ellipse that could be touching any single point. So definitely a possibility. So we've got an ellipse, and we have a line that meets it in just one place. Lots of options, so that's definitely a possibility. And we have the same types of possibilities with this one. Right? We could have 0, 1, or 2 solutions, depending on how the line meets the parabola, or it doesn't meet it. All right, so let's go ahead and do this one. It's just a little word problem. It's not that complicated. So we have a rectangular sign that has an area of 2 yards. We've got some rectangular sign. The area is 2 yards. We know that the area is base times height, or length times width. So we know that the height times the base is 2. We know the perimeter is 6, which means the semi-perimeter is 3. So this gives us a system, a nonlinear system. Semi-perimeter is just the sum of 1 base and 1 height. So if the perimeter is 6, then half the perimeter, also called the semi-perimeter, is 3. So nonlinear system. Find the dimensions. This is not too hard. We're going to solve the top equation for h. We're going to plug it into the second equation and solve for b. So we have b over 2 plus b equals 3. So it tells us that we have 3 halves b equals 3. So b will equal 2. And if b is 2, h is 1, so we get h equals 1 with units yards. And b is 2 yards. Not too bad. It feels a little too easy, though. Very straightforward nonlinear system. One more. You guys work on this one. It's not that these are hard. They're just trying to give us a couple of applications where you are dealing with nonlinear systems. It's December. Shouldn't be looking at that. Is today December 1st? Sure. Yeah, exactly. Common denominator of 2. You could do that too. Or you can think it was 1b plus half of b is 1.5b.
We'll find that too. Absolutely, because that 2 will multiply by that, multiply by that. So I have 3b is 6. Absolutely.
Totally fine way to do it. Invoke Pythagoras. No doubt. What are you doing? Yeah, that would be square. That would work. But that doesn't give us a diagonal of 3, 5. So put your letter here, face in your body. Come on, Wilson. Base height. Pythagorean theorem. Oh, there, now I see. No, you're doing the right one. No. Yeah, now I see it. No, you're cruising. Cruising! With these applications, I was thinking of that's good. It's a good habit to be in. Did you let X be the horizontal and Y be the vertical? All right, so we're going to deal with a rectangle here, and the answer might be a square. We don't know. It won't actually turn out to be a square in this case. So they tell us this information. They tell us that the diagonal is going to be √5 meters. And they also tell us that the perimeter is 6. So whatever we want to call the base and the height, X and Y, B and H, whatever, L and W. Regardless, we get 2 equations. We have a system. We have the semi-perimeter is 3. If the whole perimeter is 6, then half the perimeter is 3. It's semi-perimeter. And then we also have, from the Pythagorean theorem here, we have this right triangle. So there's the nonlinear equation that we're dealing with. X squared plus y squared will be equal to 5. So there's our nonlinear system. Now not too earth-shattering. We can solve for x or we can solve for y, doesn't matter. So if we solve that for x, then we take it and substitute it into the second equation. We're going to have 3 minus y quantity squared. So that's 9 minus 6y plus y squared equals 5. Nonlinear means everything to one side and factor. That's 2y squared minus 6y. Subtract the 5 and we get 4. Definitely divide out a 2. If you can divide out a common factor, it's always easier. And then that factors nicely. Y minus 2 and y minus 1. So we get y equals 1 or y equals 2. And if we plug it back into which equation should we plug into? The linear or the quadratic? Linear for sure. So if we plug in y equals 1, that tells us that x is going to equal 2. If we plug in y equals 2, we get that x is equal to 1. And so it just boils down to the fact that our garden is going to be 2 meters by 1 meter. That'll be our answer. 2 meters by 1 meter. Yeah? Oh, we didn't factor out, I divided it out. Yeah, no, that's fine. So because the other side is 0, 2 goes into 0 0 times. Yeah. Mm-hmm. So we divide it away. Eliminate it. Okay, so let's talk a little bit about a week from today, the test.
So let me open up the test. The moment of truth.
You said we were going to get some kind of study guide?
Yep, and this study guide is coming, and I said I would give you a formula sheet. Is that what you're talking about, formula sheet or study guide? Both. Okay, so the formula sheet is now posted. If you go into D2L, log in again, okay. So in D2L, you will find the formula sheet. Under content, and where did I put it? Right there. So it's under exams and keys, right there, formula sheet. So I will bring copies of that. You don't need to print it out and bring it. I'll bring copies of it for you. But this is so you know exactly what's going to be on it. It's 2 pages. All that stuff's on it. A lot of stuff. So much stuff. Okay, let's talk about what's on the exam first.
So we had 4 exams. So those 4 exams, I'll just copy and paste right off those 4 exams and then change the numbers. So the wording will be identical, the question will be identical. I'm just going to change the numbers or the functions. So from each of the first 4 exams, there'll be 3 or 4 from each. So to study for that content, obviously you should just study those exams. And the answer keys are all posted in there. So in D2L under exams and exam keys, there is a key posted for each exam. So that is definitely where you want to be going to study the review content. So there's a key up here for each exam, all the way through, all 4. The content from 5 and 10 I'm going to tell you right now. So there's only 3 or 4 questions from chapter 5. There's only 3 or 4 from chapter 10. There's not a ton. And here's what there will be. So in 5.2, in chapter 5, we had logs and exponentials. Can I get that all on there? Okay. Down there it just says be able to solve equations. All right. And that's going to be super important. As you go into calculus, being able to solve a log equation or an exponential equation, that's really important. So this 5.5, definitely important. Being able to solve equations. Oh, it's in bold. I wonder why. 5.2. All we do is graph basic exponentials and then shift them around. 5.3, we graph logs and shifted them around. And then we had the change of base formula. I'm not going to put a change of base formula on there. That's not really, there's bigger fish to fry. Poor fish. The section 5.4, this one's important. There's a lot of those log rules. So you take several log expressions and you combine them into one. You take one log expression and you expand them. Those are important skills to have going into calculus. So definitely practice that stuff. Most of that is really straightforward. This section is the most important, though. I would definitely say that's the most important in chapter 5. Because it can be ambiguous how you solve an equation. So we'll look at a few and do some practice. In any of these sections, you can go into my math lab, you can go to the study plan, you can go to the section, and you can go to any one of these objectives and practice as much as you want. Chapter 10, we had 4 topics, and there's only 3 or 4 questions. So, parabola, ellipse, hyperbola, nonlinear system. Got to be one of each. Right? So, nothing nothing surprising there. If I was going to leave any one of these graphs off, so I could ask 2 questions on one of the other ones, what graph would I probably leave off? The ellipse. Those are the easiest of them. So definitely make sure parabolas and hyperbolas. Those are the ones that take a little more ingenuity, so practice those. And then a nonlinear system. It's very common in calculus where you have to figure out where 2 curves intersect so that you can find area or whatever the concept is in calculus you're working with. So I think what I want to do today, we pretty much did this page today. We did a bunch of parabolas, we did a bunch of hyperbolas, and we did a bunch of systems. So today's notes are a really good set of notes to look at for practicing chapter 10 material. And of course, practice some other stuff too. So chapter 5, let's focus. Let's do a few problems from chapter 5. And again, you've seen logs and exponentials before, so I want to focus on the equation stuff. So let's solve a few of those. And let's see, I'll go through that stuff next week. Let me just pull up a blank slide. And let's start with some common types of exponential and log equations. So if we have something like this, this is a pretty standard type of equation. And you obviously want to look at the bases, and if you can equate the bases, that's a great way to go. And most of you could do that, I think, pretty easily if the bases. So, for example, if I just modify this a little bit, if I made it that, totally different methods for solution here. The one on the right is way easier. We would rewrite the 4 as 2 to the 2. And then what do we do with power to power? Multiply. When you have a power to a power, you multiply exponents. And so here we would have 2x plus 4. And then we just equate the exponents. So that's the simplest type of exponential equation. If you can't equate the bases, go ahead and do it. Obviously, you need to be able to do that. Subtract 2x, we get x. Add 1, we get 5. So we get x is equal to 5 there. Okay, so that's the simplest type, but more common is this type of equation over here where you can't equate the bases, so we have to do what to both sides?
Log.
Log of both sides, exactly. And most of the time, our preference is to use the natural log. So we're going to take the natural log of both sides of the equation. And then what do we do with those powers?
They drop down to the left.
Yep, they come down in front as multipliers. And here's one of the most common mistakes. Those powers, both of them, are binomials. So when you bring those down, you have to make sure that they stay wrapped up in parentheses. You don't want to lose. For example, I don't want to write that. Because there it looks like the natural log of 4 is only being multiplied by the 2 and not being multiplied by the x. Listen. We have to remember that the entire exponent is being multiplied by that base. Similarly on the right, so wrap that exponent up as you bring it down. Now, it may not look like it, but that's just a linear equation. It's a linear equation. The power on the x is 1. That's just a linear equation. Just because there's logs in there, it may look more complicated, but it's just a linear equation. And with linear equations, x is to one side, numbers to the other. Unlike a nonlinear equation where everything comes to one side and you factor. So let's clear the parentheses. And we see that we have two terms that involve x and two terms that are constant. Those two terms have an x in them. These two terms are constant. So we're going to bring the two x terms to the left, the two constant terms to the right. So we have x ln 4 minus 3x ln 3 equals minus 2 ln 4 minus ln 3. And then what do we do on the left? Factor out the x. Exactly. We need to isolate x. So in order to isolate x, it can only be showing up one time. It's showing up twice there, so to make it show up once, we factor. And now there's some log rules that you could apply with those expressions on the right. Unless you're asked to combine logs and do stuff, you don't need to. For an equation, if you want to leave that like that, that's fine. You could absolutely pull that -2 up and make that a 1/16 in here. You can do that. You can pull that minus up if you want, make that a 1/3, or you could make this into a fraction. Several things you could do there, but for solving an equation, that's not the skill I'm looking to test you on. So this right here is our exact answer. So that is exact. Now, if you're asked for an approximate answer, let's get the approximate answer also and make sure you can type that into your calculator without making an error. So I'm going to type it in. The entire numerator has to be wrapped in parentheses, and each individual log is going to need its argument, in other words, what's inside it, wrapped in parentheses also. So make sure that you can get the right answer. So if we go to 2 decimal places, well, let me go to 4 decimal places, 0, 2, 7, 3. So that's the approximate answer. It may look more precise because you can kind of visualize it. Oh, it's just a little more than 2. But that's still an approximate answer. That's the exact answer. This approximation has 2 P's. Okay. 2 P's. Approximately 2 P's. All of a sudden, it looks like that's way too many consonants in a row. It does have 2 P's, right? Yes. Yes. Okay. Thank you. All right. Let's take a look at a really classic log equation. So a really common type of log equation looks like this. So let's suppose we have log base 4 of x plus log base, actually I'll probably make a mistake and make it 200. Let's do it minus. X minus 3 equals 2. Yeah, the base, yeah, that's base 4 also, thank you. So log base 4 of x minus log base 4 of x minus 3 equals 2. Pretty common type of log equation that you may contend with. Now certainly if the other side, the right side, if it had a log on it, again, that would be a different way to solve. If you have the log with the same base on each side, you can then equate the insides. The guts must be equal if the bases are equal. Okay, here we're going to use a log property though. This will be log of x over x minus 3 is equal to 2. And the next step is where the most common mistakes occur. So the next step is the step that you really want to be thoughtful with. We're dealing with a log equation. We're trying to solve for x. It's buried inside the log. So what we're going to do is convert it to some sort of exponential. And what we have to remember is this spiraling thing. So the base of the log on the left here, raised to that power, will equal the inside. So our next step here is x over x minus 3 is equal 4 to the 2. So there's the exponential form of that. So then we have x over x minus 3 is equal to 16, 4 squared. So make sure that step is logical to you. That's the most common place for mistakes to occur. This is a linear equation. If we multiply both sides by x minus 3, we get 16x minus 48. Subtract off the 16x, so we get negative 15x equals negative 48. X will be 48 over 15. Cancel a 3 out. And 16 fits. Okay. Now with log equations, anytime you're dealing with a log equation, you have to go back and make sure that your answer, or your potential answer, you have to make sure that it doesn't create a log argument that's less than or equal to 0. Because logs are only defined if the argument is greater than 0, if it's positive. So we just check, loose check. 16 fifths there, that's positive. 16 fifths, which is a little more than 3, minus 3 will still be positive. So that's the extent of the check. So that is our one answer. The only answer.
It can't equal 0 or negative, right?
Mm-hmm. Okay. So it has to be positive. So after you plug that value in, you have to be left. After you plug it in and subtract 3 or whatever it says to do, you've got to be left with a positive number in the parentheses on the inside of the log. Must be positive. Okay, let's do one graphing of a log. This also is sometimes put a minus there, so something like that. The basic function here, let me call it f. The basic function here is log base 5 of x. That's our basic function. And to do anything, any graphing with transformed logs or exponentials, you have to have the graphing of the basic function down pat. You've got to be able to do that really quickly and efficiently and confidently. And so we can go through the process. We know the general idea in your mind for a basic log, if it's logarithmic growth, is that. If you can see that. Or a wave. Should look like a wave on the beach. And if you need sound effects, I got you. Sound effects are good. All right. And logs we've seen, they're basic logs, they all go through that point. And if you can just write the graph down right away, do it. And I would expect by now that most of you should be able to just sort of look in your head and say, oh yeah, I need an x value of 5 for this to be equal to 1. So I go out to 5 before I'm up to 1. And then we know there's some fractional piece over here. So if it's not 100% clear on how you get those 3 points, you plug in 3 x values. And the 3 x values that I've been telling you to plug in, you use whatever the base is, and then exponents of -1, 0, and 1. And then what do the 3 y values end up being? Those are the x values. So if you simplify those x's, that's 1/5, 1, and 5. But what are the y values? -1, 0, and 1. Right? So that's why we choose to plug in little exponentials with base 5, because the log has a base 5, so then we get the log property that collapses to just the exponent. So we pick these x's. If that was base 7, we pick 7 to the -1, 7 to the 0, and 7 to the 1. We pick that so that we get cancellation and just get nice simple y values. So then this first x value of 1/5 has a y value of -1. And then 1, 0 on all basic logs, and then 5, 1. So there is the graph of our basic function. And it doesn't have an asymptote, right? It just grows forever, but it grows really slow, but it's creeping up. It's growing forever. Okay, so then let's take a look at our transformations. Horizontal transformations, those happen on the inside. There's only one, and that's on what? Shift where? Yeah, shift right 2. So that's the only horizontal transformation. Vertical, we have 2 of them. So we look on the outside, and we read left to right. So the first transformation is reflection, and then shift up of 1. Okay, so we do the horizontals first. So we're going to shift right 2 units. So this whole graph gets shifted right 2 units, which means the vertical asymptotes get shifted right 2 units. We're going to shift to the right. The vertical asymptote comes along to the right. And we're shifting 2 units, so that point comes right over here. That point comes there. And this was 5, 1. So we're shifting 2 units. We need to move out there 2 places. There. So yeah. Not good. Okay, so there's all that step 2. There's step 2. And then we reflect For which axis? X, it's a vertical reflection, so we're going through the x-axis. And that's just going to flip it like that. That'll be step 3. And then step 4, the last step, we're going to just take that and shift it up 1 unit. So it's going to look something like that. More or less. If you need to do it on multiple graphs, do it on multiple graphs if it feels too cluttered. But be able to graph those basic logs and then transform them. Anyone have a question before we head out? December. Crazy. All right. Have a good weekend. Don't put off your studying. Get those answer keys available so you can practice. And I'll see you all on Tuesday.